Welcome again to Nursing Research 2. This time I'll be giving a review on the introduction to inferential statistics. We have same set of learning objectives. Allow me to read it again. First is to provide a quick review on descriptive statistics, which was done earlier. Second, to have a better understanding on how to interpret data gathered from a research study. Third, to know more what is inferential statistics and how it is being used in research. And lastly, to equip learners better understanding of the data interpretation using appropriate statistical techniques. Descriptive statistics are useful for summarizing data, but researchers usually do more than simply describe. So inferential statistics, which are based on the laws of probability, provide a means for drawing conclusions about a population given data from a sample. For sampling distributions, when using a sample to estimate population characteristics, it is important to obtain a sample that is representative, and a random sampling is the best means of securing such samples. Inferential statistics are based on the assumption of random sampling from populations, although this assumption is widely violated. Even with random sampling, however, sample characteristics are seldom identical to those of the population. Suppose we had a population of 30,000 nursing school applicants whose mean score on a standardized entrance examination was 500, with a standard deviation of 100. Now, suppose we do not know these parameters, but must estimate them based on scores from a random sample of 25 students. Should we expect a mean of exactly 500 and a standard deviation of 100 for the sample? It would be improbable to obtain identical values. Our sample mean might be, for example, 505 if we drew a completely new random sample of 25 students and computed the mean. So we might obtain a value of 497. So sample statistics fluctuate and are unequal to the population parameter because of sampling error. So researchers need a way to determine whether sample statistics are good estimates of a population parameters. So to understand the logic of inferential statistics, we must perform a mental exercise. Consider drawing a sample of 25 students from the population of applicants. So calculating a mean score, replacing the students, and drawing a new sample. So if we drew 5,000 samples, we would have 5,000 means. So that's the data points that we could use to construct a frequency polygon, as you can see from our figure 15.6. So this distribution is called a sampling distribution of the mean. A sampling distribution is theoretical because in practice, no one actually draws consecutive samples from a population and plots their means. So statisticians have shown that first, sampling distributions of means are normally distributed, and second, the mean of a sampling distribution equals the population mean. In our example, the mean of the sampling distribution is 500, the same as the population mean. Now for our estimation of parameters. So statistical inference consists of two techniques, so estimation of parameters and hypothesis testing. So for parameter estimations are infrequently presented in nursing research reports, but that situation is changing. So the emphasis on EBP or evidence-based practice has heightened the interest among practitioners in learning not only whether a hypothesis was supported, but also the estimated value of population parameter and the level of accuracy of the estimate. So via parameter estimation. So most medical research journals require that estimation information be reported because it is more useful to clinicians, reflecting the view that this approach offers information about both clinical and statistical significance. So in this section, we present some general concepts relating to parameter estimation and offer some examples based on a one variable descriptive statistics. So we have the point estimation. So parameter estimation is used to estimate a parameter. For example, a mean, a proportion, or a mean difference between two groups. For example, we have experimental and control subjects. So estimation can take two forms: point estimation or interval estimation. So when we talk about point estimation, it involves calculating a single statistic to estimate the population parameter. So to continue with the earlier example, if we calculated the mean entrance examination score for a sample of 25 applicants and found that it was 510, then this would be the point estimate of the population mean. While for our confidence interval, point estimates convey no information about margin of error, and so inferences about the accuracy of the parameter estimate cannot be objectively be made. So interval estimation of a parameter is useful because it indicates a range of values within which the parameter has a specified probability of lying. So with interval estimation, researchers construct a confidence interval, or the CI, around the estimate. So the upper and lower limits are called confidence limits. So constructing a confidence interval around a sample mean establishes a range of values for the population value and the probability of being right. The estimate is made with a certain degree of confidence. So by convention, researchers usually use either a 95% or a 99% confidence interval. Now, the commonly used, the hypothesis testing. So statistical hypothesis testing provides objective criteria for deciding whether research hypothesis should be accepted as true or rejected as false. Suppose we hypothesize that maternity patients exposed to a film on breastfeeding would breastfeed longer than mothers who did not see the film. We find that the mean number of days of breastfeeding is 131.5 for 25 experimental subjects and 125.1 for 25 control subjects. Should we conclude that the hypothesis has been supported? True. Group differences are in the predicted directions, but perhaps in other sample, the group means would be nearly identical. So, two explanations for the observed outcome are possible. First, the film is truly effective in encouraging breastfeeding, or second, the difference in this sample was due to the chance factors, such as differences in the characteristics of the two groups even before the film was shown, reflecting a selection bias. So, as we continue, the null hypothesis, it may be recalled, states that there is no relationship between the independent and dependent variables. So, statistical hypothesis testing is basically a process of disproof or rejection. So, it cannot be demonstrated directly that the research hypothesis is correct. It should be tested first. So, therefore, the rejection of the null hypothesis then is what researchers seek to accomplish through statistical tests. So, we need to use tools to really see if we should reject or accept the hypothesis. So, although null hypotheses are accepted or rejected on the basis of sample data, the hypothesis is made about population values. So the real interest in testing hypotheses, as in all statistical inference, is to use a sample to make inferences about a population. Now, for type 1 and type 2 errors. So, we have two types of errors. Researchers decide whether to accept or reject the null hypothesis by determining how probable it is that observed group differences are due to chance. Because information about the population is not available, or it cannot be asserted flatly that the null hypothesis is or is not true. So researchers must be content to say that hypotheses are either probably true or probably false. So statistical inferences are based on incomplete information. Hence, there is always a risk of making an error. That is why we always include in our recommendation future studies to be conducted. So researchers can make two types of error: rejecting a true null hypothesis or accepting a false null hypothesis. So as you can see from our figure, summarizes the possible outcomes of researchers' decisions. So researchers make a type 1 error by rejecting the null hypothesis that is in fact true. For instance, if we concluded that the film was effective in promoting breastfeeding, when in fact group differences were due to sampling error, so we would have made a type 1 error. So a false positive conclusion. Conversely, we might conclude that observed differences in breastfeeding were caused by a random sampling fluctuations when the film actually did have an effect. So acceptance of a false null hypothesis is called a type 2 error. So a false negative conclusion. Now for the level of significance. So researchers do not know when they have made an error in statistical decision making. The validity of a null hypothesis could be known only by collecting data from the population, in which case there would be no need for statistical inference. So researchers control the degree of risk for a type 1 error by selecting a level of significance, which indicates that probability of making a type 1 error. The two most frequently used levels of significance, referred to as the alpha, are 0.05 and the 0.01. So with a 0.05 significance level, we accept the risk that of 100 samples from a population, a true null hypothesis would be wrongly rejected 5 times. In 95 of 100 cases, however, a true null hypothesis would be correctly accepted. With a 0.01 significance level, the risk of making a type 1 error is lower. In only one sample out of 100 would we wrongly reject the null hypothesis. So by convention, the minimal acceptable alpha level for scientific research is 0.05. So naturally, researchers would like to reduce the risk of committing both types of error. Unfortunately, lowering the risk of a type 1 error increases the risk of a type 2 error. So the stricter the criterion for rejecting a null hypothesis, the greater the probability of accepting a false null hypothesis. However, researchers can reduce the risk of a type 2 error simply by increasing their sample size. So that is why we really encourage the students to have a bigger number of population. The bigger the number, the better. Because, of course, the probability of committing a type 2 error, referred to as the beta, so can be estimated through a power analysis. So the same procedure we mentioned in connection with our sample size. So power refers to the ability of a statistical test to detect true relationships and is the complement of beta. So that is power equals 1 to beta. So the standard criterion for an acceptable risk for a type 2 error is only 0.20. And thus, researchers ideally use a sample size that gives them a minimum power of 0.80. Now, under test of statistical significance, let's review this one. In hypothesis testing, researchers use study data to compute a test statistic. For every test statistic, there is a theoretical sampling distribution. So analogous to the sampling distribution of means. Hypothesis testing uses theoretical distributions to establish probable and improbable values for the test statistics, which are used to accept or reject the null hypothesis. In hypothesis testing, researchers assume that the null hypothesis is true and then gather evidence to disprove it. Assuming a mean percentage of 50.0 for the entire population of recently published nursing studies, a theoretical sampling distribution can be constructed. For simplicity, let us say that the standard error of the mean in this example is 2.0. So in our study, the SEM or structural equation model was actually less than 2.0. So this is shown in figure 15.8. Based on normal distribution characteristics, we can determine probable and improbable values of sample means from the population of nursing studies. If, as is assumed according to the null hypothesis, the population mean is 50%, or 50.0 or 95% of all sample means would fall between 46.0 and 54.0. So that is within about 2 standard deviations above and below the mean of 50.0. So the obtained sample mean of 75.3 lies in the region considered improbable if the null hypothesis were correct. In fact, any value greater than 54% female would be improbable if the true population mean were 50.0. So when the criterion of improbability is an alpha level of 0.05, the improbable range beyond 2 standard deviations corresponds to only 5%, or that is 100% to 95% of the sampling distribution. So in our study, the probability of obtaining a value of 75.3% female by chance alone was actually less than 1 in 10,000. We thus rejected the null hypothesis that the mean percentage of females in nursing studies was 50.0. So we would not be justified in saying that we had proved the research hypothesis because the possibility of having made a type 1 error remains. But the possibility is, in this case, remote. So researchers reporting the results of hypothesis tests state whether their findings are statistically significant. So the word significant should not be read as important or meaningful. In statistics, the term significant means that obtained results are not likely to have been the result of chance at some specified level of probability. In non-significant result means that any observed difference or relationship could have been the result of a chance of fluctuation. So we're almost done. Let's proceed with the parametric and non-parametric test. So most tests that we discuss in this part, and also most tests used by researchers, are parametric tests. So parametric tests have 3 attributes. They, first, focus on population parameters. Second, involve certain assumptions about variables being analyzed, such as the assumption that they are normally distributed in the population. And lastly, the third one, require measurements on at least an interval scale. For the non-parametric test, by contrast, do not estimate parameters and involve less restrictive assumptions about the shape of the distribution of the critical variables. In non-parametric tests are most often used when the data have been measured on nominal or ordinal scale, or when the data distribution is markedly skewed, or when the sample size is too small to be confident about the shape of the distribution. So parametric tests are more powerful than non-parametric tests and are generally preferred when variables are measured on at least the interval scale and the sample size is not small. Now, lastly, talking about the overview of a hypothesis testing procedures. So, in the next section, a few statistical procedures for testing research hypotheses are discussed. So, the emphasis is on explaining applications of statistical tests and on interpreting their meaning rather than on explaining computations. So, each statistical test has a particular application and can be used only with certain kinds of data. However, the overall process of testing hypotheses is basically the same for all tests. So the steps that researchers take are the following. Step 1, selecting a test statistic. So researchers select a test based on such factors as whether a parametric test is justified, which levels of measurement were used, and if relevant, how many groups were being compared. Step 2, specifying the level of significance. An alpha level of 0.05 is usually chosen, but sometimes the level is set more stringently at 0.01. Step 3, computing a test statistic. So researchers then calculate a test statistic based on the collected data. Our fourth step, determining degrees of freedom. This is very important, the DF or the degrees of freedom. So the term degrees of freedom or DF is used throughout hypothesis testing to refer to the number of observations free to vary about a parameter. So the concept is too complex for full elaboration here, but computing degrees of freedom is very easy. And the last final step, or our fifth step, comparing the test statistic to a tabled value. Theoretical distributions have been developed for all test statistics, and values for these distributions are available in tables for specified degrees of freedom and level of significance. The tabled value enables researchers to determine whether the computed value is beyond what is probable if the null hypothesis is true. If the absolute value of the computed statistic is larger than the tabled value, the results are statistically significant. If the computed value is smaller, of course, the results are non-significant. So that finally ends my review of our topics of inferential statistics. So I hope you learned something and you were reviewed, and it will aid you in finalizing your chapter 4. So thank you for listening. That ends our discussion.